All right, we're diving into one of the biggest, most fascinating puzzles in AI today, and it comes straight out of the NeurIPS 2025 workshop. The question is this: how do we build foundation models that don't just get built once, but actually get better forever? How do we finally build AI that keeps up with our world?
I mean, really think about it for a second. We've built these absolutely incredible models, right? They're like digital geniuses that have read pretty much the entire internet. But here's the catch. The very moment their training stops, they're completely frozen in time. So the world keeps changing, but they don't. And that's turning into a massive and really expensive problem.
And this right here is the core challenge that the whole AI community is grappling with now. Look, we've gotten unbelievably good at building these giant static models. But the new frontier, the next big thing, it isn't just about training them anymore. It's about maintaining them, keeping them alive and relevant in a world that never, ever stops changing.
Yeah, and this slide just lays it all out perfectly. On the left, you've got the old way of thinking. You build a static model, and over time, it just decays. It becomes a relic. But on the right, that's the new goal, a dynamic system that's always learning, almost like it's a living thing. We're fundamentally shifting from just building a product to actually managing a process. So what happens when we get stuck in that old way of doing things? Well, we run into these two villains. First, you've got model decay. That's when the AI's knowledge gets stale and its performance just starts to tank. Then there's version skew. This is the absolute chaos that ensues when you have multiple, slightly different versions of a model out there, all giving you unpredictable, incompatible results. And trust me, both of these are incredibly expensive problems to have.
So, how do we actually fight these villains?
Well, the first line of attack is architectural. It's all about rethinking the very structure of these models. It's like we need to perform a kind of high-tech brain surgery to update them efficiently without having to start from scratch every single time. And that leads us right to our first big puzzle. How in the world do we change what a model knows or how it behaves without doing a full, billion-dollar retraining? We need methods that are both surgically precise and actually affordable. Okay, so the first big breakthrough is a technique called IPA, and it actually won Best Paper. It solves a really key flaw in popular methods like LoRA. See, to be efficient, LoRA has to kind of randomly throw away some information when it doesn't update. But IPA is way smarter. It actually analyzes the information first to figure out what's important before it makes that update more compact. And the result is just stunning. It matches LoRA's performance with about half the parameters. I mean, that is a huge win for efficiency. Now for the next innovation, which is called HyperAdapt. LoRA is great, but it's low rank, which basically means it's not very good at making really complex, deep changes to the model. HyperAdapt gets around this. Instead of adding a bunch of complex new stuff, it just scales the existing weights. The best way to think about it is like having thousands of tiny little volume knobs on all the model's neurons. This lets you make incredibly complex, high-rank updates using very, very few new parameters. And this number just shows you the power of that approach. In some cases, HyperAdapt can pull off these complex updates using up to 34 times fewer trainable parameters than LoRA. Seriously, for any team that's deploying models at scale, a number like that completely changes the economic equation of keeping your AI up to date. Okay, so we've got ways to make cheaper, more powerful updates. That's awesome. But that really only solves half the problem. Now we've got to face an even trickier puzzle. How do we teach an AI something new without it forgetting what it already knows?
This is the classic problem of what's called catastrophic forgetting. It's a huge deal. You fine-tune a model on some new data, and then all of a sudden, it can't do the things it was an expert at yesterday. It's kind of like teaching a brilliant surgeon how to paint, and in the process, they forget how to perform surgery. It's a massive barrier if we ever want to create models that can truly learn continuously over time.
So a new guiding principle called RL's Razor offers a way forward. It turns out that a specific kind of reinforcement learning is just inherently safer for making updates. And why is that? Well, because it's naturally designed to find the smallest possible change it needs to make to learn something new. It acts more like a careful surgeon, always taking the path of least resistance to preserve everything the model already knows. So, here's the crucial insight, the big takeaway. It's not just about what new information you feed the model. How you teach it, the update mechanism you use, is just as, if not more, important for preventing that catastrophic forgetting. It's the key to making sure the model stays stable and coherent over its entire lifetime.
But what if we could just avoid all this risky brain surgery in the first place? Well, that's the radical idea behind something called limited memory language models, or LMLM. This new architecture basically splits the model in two. You have one part for reasoning, and then a totally separate external database for all the facts. The model is then trained to just look up facts when it needs them, instead of trying to memorize everything.
Honestly, the best way to think about this is that we're giving the AI a cheat sheet. Instead of trying to cram every single fact into its head, which is super risky to update, we just give it an external notebook. So if you need to update a fact or even make the model unlearn something, you don't perform dangerous surgery on its brain, you just edit the notes. It's instant, it's verifiable, and it's safe.
So when you put all of these pieces together, the efficient updates, the safe learning principles, and this idea of externalized knowledge, you get a really profound shift. We're moving away from just building these standalone AI models and entering a completely new era of orchestrating living, evolving AI ecosystems. And this is what the workshop started calling operational AI.
So, let's just quickly recap the 4 most impactful breakthroughs we talked about. First, we've got those efficient updates with methods like IPA that let us do more with less. Second, the absolute game changer of knowledge externalization with LLM. Third, the idea of safe learning, guided by that RL's razor principle. And fourth, the incredible power of high-rank efficiency that we saw with HyperAdapt.
And of course, this incredible progress doesn't just happen in a vacuum. This work is being driven by a total powerhouse of academic and corporate labs. You've got MIT, Google, Amazon, and so many others. This just gives you a little taste of the key players who are really defining this new frontier of operational AI. Okay, so this is all fascinating research, but let's get down to it. Why does any of this matter to you if you're out there actually building things with AI? Let's translate these concepts into some real concrete advantages, especially for those of you building the next generation of autonomous agents.
Let's connect the dots. IPA? That gives you stable backbones for your agents, so updates don't break their core skills. LMLM? That enables instant refresh, which is absolutely critical for an agent that has to operate in a changing environment. RL's Razor provides the blueprint for safe learning, letting you adapt your agent to users without it forgetting its safety protocols. And then techniques like HyperAdapt? They allow for on-the-fly adapting, letting agents specialize for new tasks in real time.
So, we are solving the technical puzzles. We're getting closer and closer to creating AI that can learn forever, systems that can truly be a part of our world. But all of this progress leaves us with one final, profound question. As we build these perpetual learning machines, the most important decision isn't just what they learn, but who gets to decide, who gets to be the teacher.